Welcome back to week 2 of the problem solving session for the Introduction to Fluid Mechanics course. First of all, I hope that I'm audible. So, because sometimes in the feedback I see that people say the voice is too low or like it's not clear. So, just let me know whether the voice is audible or not. You can write in a chat box or thumbs up, like anything you can just suggest. Thank you. Sorry. Okay, so I hope all of you are doing well. So let's start. Meanwhile, other students can join as well. So just to clarify, last week I think there was a doubt regarding the representation of the tensor vector for a cylindrical coordinate system. So I think I clarified that doubt last week as well. Like last week only, like initially I thought that I had some doubt, but last week only I told that it was like something like you replace the indices for the Cartesian coordinates to the cylindrical coordinates. So I hope the person who asked the doubt is here. If he is here, he can just let me know, or else like
Yes, sir.
okay, just okay then. So just to reiterate, you asked a good doubt only that how to represent tensor vector for the cylindrical coordinate system. So I initially I was a bit skeptical because I thought that there might be a coupling, but between the cylindrical coordinates, because there's a coupling between the r and the theta coordinate, but that coupling arises when we consider derivatives. So that coupling will become highly relevant when we consider the derivation of the Navier-Stokes equation. Okay, if you don't, any one of you don't know, Navier-Stokes is the governing equation for the fluid flow. So if when we encounter Navier-Stokes and try to solve the analytical solution for Navier-Stokes, then we'll see that there are some coupling terms arising in the cylindrical and the spherical coordinate systems. But since we are not doing any kind of derivatives, at least while doing the transformations, so there will be no such coupling term arising when we transform from the cylindrical. So just let me complete from the Cartesian to the cylindrical coordinate system. That's why to get the tensor vector for the cylindrical coordinate system, you just need to replace the indices from xy to r theta, or xyz to r theta and z, and I cap, j cap, k cap to e r cap, e theta cap, and e z cap, and similar for the spherical coordinates. There's all the transformation. Is it okay? Kindly provide the PPT in PDF format. So just to look into the doubt. Okay, okay, Mani Kanchan, what PPT are you talking about? Can you please let us know? Meanwhile, uh, I think it was power, right? The doubt. So is the doubt clear?
Yes, sir. Yes, sir.
Okay. Thank you so much. Okay, so Mani Kanchan, you can. Meanwhile, if you want, you can just write the doubt in the chat box. So I will just start today's session. So I think we are running a bit late. So okay, okay. So continuing, I think the last week sessions were quite the last week contents or discussion were quite clear. So similar to the last week, just to reiterate, I will briefly go through the concepts that were discussed in the week 2 by Professor Suman Chakraborty. So I will briefly go through the concepts. Of course, I won't do much elaboration, but there might be some doubts. So if there are any doubts, I would like to address them in there itself. But if there are some elaborate doubts, like which I don't know at that moment, so I will try to look into it for this week, and maybe we can clarify it in the next week's session. So with that, I think we can start. So this week's contents are a bit more elaborative, like more or less like the content is a bit more than the last week. So I will try to go a bit fast, but if there's any confusion, you can just let me know. And after this, of course, after the discussion of the topics, we'll go through some questions that are relevant to your assignments and your exams. Okay. So we continue our discussion on the continuum hypothesis. like last week we discussed about the concept of the continuum and why the continuum hypothesis is important while discussing fluid mechanics. So I think we made it clear because we need to deal with derivatives and integration on all kind of calculus while describing the fluid flow systems in an analytical manner. That's why we need that the functions, for example, the velocity or the pressure that we're considering, should be constant. Sorry, not constant. Should be continuously differentiable. Okay, basically they should act like good functions. So, and that clarity or that kind of behavior comes when we consider the behavior of this velocity field to be continuous, and that will come when the particles that constitute the velocity field are close enough with each other so that we can approximate their behavior as a continuous. Okay, so we will see that implication on today's discussion. For example, we start with the definition of density. I think that's quite clear. We usually define density by mass per unit volume. Okay, that's a very trivial and simple definition. But Professor Chakraborty again piques our interest by looking into a very good observation. That is, when we say mass per unit volume, what should be the volume that we are considering while defining density? Okay, so we are showing here like there is a very small mass by very small volume. We define density like that, and what should be the small volume? Okay, so Professor Chakraborty says that this small volume, although we say the limit delta V tends to 0, it should actually not approach 0 explicitly. Why? Because if it approaches 0, then this will shoot up. Okay, it will go to infinity, which is not correct. So from the perspective of fluid mechanics, this delta V should approach actually a value of delta V star be up to which or beyond which the continuum hypothesis is valid. Or like if you go lower than this delta V star, then the continuum hypothesis will no longer be valid. So we don't want those kind of values. So what happens is that if we consider a very scarcely populated region with fluid particles, or very rarefied system where the fluid particles are very far away from each other, then if we consider those kind of systems and then we evaluate density, then we will see that the density value will fluctuate from one value to another, and which we don't want. We want the density to be constant. Like for example, if we are not considering highly compressible flows, which will be at least the flow regime that we are considering. We will consider, for this course we will only consider incompressible flow regime for most of the cases. So in those regimes we will want that our density should behave as a good function. Like it should not fluctuate rapidly or should show variable nature. It should show a constant value for a given choice of delta V, and the delta V should fall below, like I must say, should fall in this range. That it shouldn't be smaller than this delta V star, like below which the continuum hypothesis breaks down, and also it shouldn't be that much large, which would again show local variations. Okay, so we don't want those kind of those scale of volume or length scales for discussing the value of density. And density is just an example. Like any kind of flow of behavior, when we measure, we would like to, like if you're considering measurements that constitute per unit mass or per unit volume, this kind of measurements, we would want that those measurements should follow between these length scales. Okay, so that's what the basic concept is, and it's just an application of the continuum hypothesis. And from now on, I think we won't really emphasize upon the validity or the importance of continuum hypothesis. We'll just agree upon that the continuum hypothesis is valid for all our discussions. Okay, so I think that would be the end of the explicit discussion on continuum hypothesis for this course. So then we define another fluid flow property, that is bulk modulus. I think we did an example last week that discussed about bulk modulus. So it's basically the change in pressure divided by the volumetric strain, or the ratio of change in volume by the original volume. And we consider negative sign because we consider that the pressure would exert a compressive force. That is, it will reduce the final volume. That's why delta V would be negative. So this negative and negative side will cancel out and we'll get a positive value for K, that is the bulk modulus. So then we look upon a expression that basically quantifies this compressibility. Like we discussed about, I only discussed right now about that we will consider about flows that are incompressible, but there must be a quantifying factor or parameter range beyond which the compressibility effects become considerable, that we cannot disregard it. So what is that range? So to do that, we'll just briefly go through a small derivation that was again discussed in the lectures. So we consider mass to be density times volume. Okay, now we know it. We already discussed it a few moments ahead before. So we'll take the natural log of this equation on both sides. So we'll have ln m is equal to ln rho plus ln v. We'll take the derivative. Then since mass is conserved, or mass won't change, we will have m equal to 0. The derivative of this term would be 0 because dm will be 0. Then it will be d rho by rho and dv by v. Okay, the derivative of this natural log term will come out to be this. Then when we just like we can represent d rho by rho in terms of dv by v. So we'll have d rho by rho to be minus dv by v. We'll see why we did that. So we know that the definition of bulk modulus is k is equal to minus delta p delta v by v, right? So we can just replace this delta v by v in terms of delta rho by rho. So we saw that delta rho by rho is negative of delta v by v, so the negative sign will be cancelled out here. And again, it's understood that if a mass, or if a if a certain mass of any matter is compressed to a lower volume than its initial volume, then we'll assume that if there is no leakage through that matter, then the density of the matter should essentially increase if the volume is decreased. And more or less, if the mass is conserved and if the volume is decreasing, then the density should essentially increase. That's why if there's any change in the volume that which causes the volume to go down, then the density should go up. Okay, that's why again it physically makes sense, and mathematically also we have just proven it. Okay, so we just replace del v by v by del rho by rho. So we can write k is equal to rho times del p by del rho. Now this change in pressure, this delta p, Professor Chakraborty says that it scales as half rho u square. And I don't know whether in this course we will discuss about the scales or characteristic scales of pressure. If you recall, we just discussed about the characteristic length scales of flow in the previous class, where we told that the length scale across which there is a considerable change in the velocity. Similarly, there must be a characteristic length scale of pressure as well, where or the range of pressure across which there is a considerable change in the flow behavior. Okay, so for most of the cases, and considering that we are considering a general flow where both the inertial and the viscous effects are considerably equal, then in that case our pressure should usually scale as half rho u square. Okay, and we will see this scaling when we discuss about Bernoulli's principle in the later part of this course. You will see that we will again come to the scenario where pressure would scale as half rho u square. Okay, but again, just to be specific, if any one of you of course might be doing advanced fluid mechanics studies as well, so they might know that in some scenarios pressure scales as the viscous scales as well. It will be, I don't remember the exact expression, but it will depend on the viscosity as well. Okay, sometimes in some kind of flows where the viscous effects dominates over the inertial effects, so in those scenarios your pressure may scale with viscosity as well. Okay, so just to specify those scenarios, and not disregarding or just explicitly saying that pressure always scales as velocity, but for most of our study, at least in this course, pressure would usually scale with the square of velocity, that is half rho u square. Okay, then if you just substitute this expression back here, you will get that k, that is bulk bulk modulus is or is similar to or very similar to rho square u square by 2 times delta rho. And if you rearrange these terms, just rearranging the terms, you can see delta rho by rho varies as half times rho u square by k. Okay, now k by rho, this bulk modulus by the density, the square root of bulk modulus by density, gives us a very interesting parameter that is known as the speed of sound in the medium. Okay, so you might have heard about supersonic jets, supersonic what to say, fighter jets, right? So the word supersonic usually means that the speed of that jet or flight is higher than the speed of sound. And we in specific, you must say speed of sound in that medium. And since the fighter jet is traveling in air, so we should say that speed is the speed of the jet is higher than the speed of sound in air. So since we are not specifying any medium, and of course this medium has to be a fluid because we are discussing fluid mechanics, so it might be liquid as well or gas as well. Okay, so we are just saying a medium. So the ratio of square root of k, the square root of the ratio of k by rho gives us the speed of sound in that particular medium. Basically the speed at which the disturbances propagate in that particular medium. Okay, so we will have delta rho by rho. Then if you just substitute this expression here, you will get delta rho by rho to vary as half u square by c square. Now this u by c again gives us a very interesting parameter which is known as the Mach number. Okay, and again you will see, since both u and c are velocities, this is basically a non-dimensional parameter or a non-dimensional number. So in the first class we discussed about Knudsen number, to be one of the first non-dimensional numbers that we usually get introduced in fluid mechanics. Similarly, Mach number is another such non-dimensional number that is useful to characterize fluid flow problems, and it becomes much more relevant when we discuss about compressible flows. So this is the parameter, as I discussed before this derivation, that is used to characterize the compressibility of the flow. So if this Mach number is high, we say that the flow is more compressible. Okay, so you see that delta rho by rho varies as half rho ma square. So if ma is high, then the change in delta rho is higher, right? So we want that if the change in delta rho by rho is less than 5%, okay, then we say that the flow is essentially incompressible. And in that case, this usually comes around Mach number to be 0.3. Like if the Mach number is lower than 0.3, we consider that the flow is essentially incompressible. Okay, and from 0.3 to 0 to 1, we consider the flow to be in the transitional state. We neither say it is highly incompressible or compressible. But beyond 1, Mach number equal to 1, we say that the flow has become supersonic. Okay, so the term that the speed of the jet is higher than the sound velocity in that medium, or the flight is supersonic, it basically means that it is traveling, the Mach number for that particular the velocity of the flight which corresponds to a particular Mach number is higher than 1. Okay, so I hope it is clear till now. If there is any doubt, you might ask. Just to reiterate, we won't be dealing with incompressible flows for this course, but again, it's an important parameter to know. Like if someone asks, okay, you studied, okay, sure, Anjali, you can ask a doubt.
So I wanted to ask that in one of the equation you have written delta P is equivalent to half rho u square. Can you just give a small short description from where does it come?
Okay, so okay, thank you. Let us just look into it. Again, it's a very actually elaborate question, but let me try to answer it. Okay, so if you look into it, first of all, let us just check the scales. Okay, so we have delta P, change in pressure. So pressure would be force per unit area, kg meter per second square divided by, I think you can do an exercise for me, all of you. Check the units for this, and rho is kg per meter cube and meter square second square, right? So just check whether the units of both of these are consistent or not. Okay, it seems consistent for me. So dimensionality wise, pressure, the variation of pressure can be scaled as half rho u square. Okay, so dimensional homogeneity tells us that this scaling is alright. So the question that you asked actually stems from a very important factor. So I don't know whether you know about the Navier-Stokes equation or not. So Anjali, I'm asking, do you know about Navier-Stokes equation?
Yes, I know about Navier-Stokes equation, but I'm not fully aware about the derivation of the Navier-Stokes equation.
Okay, very well. Okay, so in the last class, if you remember, I said that, for example, in a pipe flow, the characteristic length scale would usually be the diameter of the pipe. Okay, so similarly, or it will mean that our LC would vary as the diameter of the pipe. Okay, the any change of flow parameters will be interesting in this length scale. So we use this kind of scales, length scales, or just I would say measurable scales, to see how the particular parameter varies in the flow field. Okay, so while deriving the Navier-Stokes, okay, so there is a what to say derivation, or I would say there is a method where we try to non-dimensionalize this Navier-Stokes equation. Okay, non-dimensionalize the Navier-Stokes equation. So in that, when we non-dimensionalize the Navier-Stokes equation, what we have to do is we have to find a particular scale with which all the parameters vary, right? For example, just to say, if you just want to non-dimensionalize this equation, what do you have to do? You want to first see how your this velocity scales. Okay, so your non-dimensional velocity would be something like u times, say, u characteristic would give you the non-dimensional velocity. Okay, then time should also has to be non-dimensionalized. So time, I will say time by, say again, tc is t star, where t star is my non-dimensional velocity. So if you just substitute this in this back into this equation, you will get something like u star times, sorry, not u star, uc times dou u star by tc by dou t star. Okay, so this is how you get the non-dimensional form of the equation. So this term is, sorry, this is the dimensional form but this part is non-dimensional with respect to this parameter uc by tc. Okay, so we do this similar thing for all the terms, and when we discuss about the pressure term in the Navier-Stokes, which will basically be in the form of gradient of P, if you know, I don't know about other students, if they know also, let me just know. So the pressure term will be like this. Okay, minus of 1 by rho del P. Okay, so what we need is we need a scale, like how the pressure will vary. Okay, so you can say let us do P by PC to non-dimensionalize the pressure. Okay, but the question is, what is PC? PC is not something that is a characteristic of the geometry that you are considering, right? So we want PC to be in terms of either the geometry or the flow parameters. Geometry would be your length scale, and flow parameters would be your velocity and viscosity. Say viscosity I will not use nu, say mu. So the basic practice is, as I mentioned, let us scale pressure in terms of what dominates the flow. Okay, so if the flow is something like flow over a airfoil. Okay, for example, say we are considering flow over an airfoil. Okay, in those scenarios, those kind of flows are usually high Reynolds number of flows. So those kind of flows are inertia dominated. Okay, So we'll say that in that case our PC would vary as half rho u square, which basically denotes the inertial energy. Okay, the inertial energy of the flow. So I will say my pressure would scale the inertial energy because the inertial energies dominate the flow or drive the flow. But when we say for example, say very low Reynolds number flows, okay, the flows in the Stokesian regime. So in that case, the flow is usually been governed by the viscous scales or the viscous effects. So in that case, I cannot scale pressure as this one. I have to devise a scale that constitutes the viscosity, as I already mentioned. So it is how the scaling of pressure comes into picture. And it's a well-known fact actually. Like we will scale the pressure with respect to the dominating factor that drives the flow. If inertia drives the flow, we will scale pressure with inertia. If viscosity drives the flow, we will, or the viscous effects drives the flow, we will scale pressure with viscosity. So this is not a universal expression, as I mentioned. It depends on the type of flow. Okay, so that's how it comes into picture. Okay, so is it fine?
Okay, sir.
Okay, I think it might sound a bit unclear, I understand, but as we proceed further in the course, you will get to know how this actually comes into picture. Okay, you'll get explicit expressions. So right now, if I go in that direction, I think it will be detrimental for like the students as well as us also. But I think if you still are unclear, you can just put that down in the discussion forum. I think I can then look into that and maybe give you some resources to look into it. Okay.
Okay, sir. First, I'll myself try to understand how these came and what is the physics behind it. And if I didn't understand, then I'll pick
Yeah.
it up.
So what I can tell you is what you can do is just try to look in the Navier-Stokes and the non-dimensionalization of Navier-Stokes. Okay, I think this will be the advanced part of any fluid mechanics textbook, and unfortunately
Okay, sir.
we won't deal with the non-dimensionalization part because this course is limited up to the initial part of the boundary layer theory and the pipe flows. But still, for your own knowledge, you can just look in the non-dimensionalization part. I think you will then directly get your answer, like how this comes into picture. Okay.
And one more thing, sir, you told that in some cases the viscous force dominates than the inertial force. Can you give an example of that?
Yeah, so I think for that, I hope all of the other members in the class are fine with this discussion. Okay, please don't mind. But these are genuine doubts, so I think I have to address it. Okay, so let me just write the Navier-Stokes equation. I think that would be much more better. I think I will use the vector form. Minus 1 by rho plus rho g. Okay, so all of you like who do not might be scared by looking to this equation, and it's understandable, but this is the equation that I was talking about so much in last class, and now also I'm talking about, and it seems Anjali already knows about it. So this is the Navier-Stokes equation. Okay, so when you non-dimensionalize it, depending upon your flow characteristics, so you will see that for example, so, and as Anjali rightly pointed out, so when are the scenarios when the viscous scales become dominant? Okay, so for example, when we consider the flow around the bacteria, okay, so bacteria are very small creatures, right? So any kind of flow, even if the flow does not have a higher viscosity, okay, let's just to clarify, even if the flow does not have higher viscosity, the motion around this kind of small macroscopic creatures is primarily dominated by inertial effects. Okay, no, sorry, dominated by the viscous effects and not the inertial effects. Okay, it all boils down to scaling. Okay, so when you don't understand, you will see that the advective terms, okay, this advective term, this is the advective term, this will usually approach 0, and there are no additional any body forces, so this will go to 0 if we don't consider gravity, like disregard gravity, and the unsteadiness also will become 0. Okay, so the only terms that remain that are dominant for the governing the motion of these microscopic creatures or small particles would be these two terms. Okay, these two terms. So if we just rewrite it, then we will have something like, oh, I just made a mistake. This should be nu, the kinematic viscosity. So we will have delta P to be equal to mu lambda square V. Okay, so now you can see that now I can think I can just write the scales as well. So now you think this is the governing equation for your motion for small particles or small microscopic creatures. Okay, this is the governing equation that we use to define their motion. So now if you just scale it, okay, just see the scales. So it will be some pressure times characteristic length scale times viscosity mu by characteristic velocity v by some characteristic length scale square. So if you do, then you will get the characteristic length scale of pressure to vary as mu Vc by Lc. So now this would be the characteristic length scale or the characteristic scale for your pressure in those kind of flows. Okay, so does this sound alright? So this is again a valid scale for the variation of pressure actually, but these are two completely different regimes, flow regimes. These are inertia dominated regime, these are viscous dominated regime.
Okay, sir, I understood.
Okay. Okay, then thank you. I hope this discussion was quite beneficial for other students as well. So for the sake of saving time, let me just proceed further. But again, after some time, if you have any doubt, you can ask. Okay. So again, there was a very interesting point that was discussed by Professor Chakraborty, which I always appreciate about him, that he, even though it's not really needed for a very basic level of fluid mechanics course, but he reiterated the difference between an incompressible flow and incompressible fluid. Okay, although it's a very one-line answers, like for incompressible flow basically means there's no change in the volume of the fluid element. Okay, but for incompressible fluid there is no change in density due to a change in pressure. Okay, so although both of them like sound quite similar, but there is again a very small, I would say, delicate difference between the two. Okay, so I won't say like any exam or this thing will explicitly ask this question, but I feel that for the exam purpose, maybe these questions might be asked, one word question that might be asked in the exam or the assignment. So I think it would be a good thing to look into it, and moreover in interviews, say if you're in bachelor's, say if you're doing masters or any job interview as well, you might, some experts who are fond of this kind of subtle differences might look into it and might ask you the difference. Okay, it's all in definition. I think there is nothing to clarify, but again the definition you have to know. Okay, so of course this note I will share, but you can look into it then. Okay, so now comes the concept of viscosity itself. Okay, so viscosity for now, essentially you can consider it something like resistance or resistive force that resists any kind of motion across the fluid. Okay, it is a very vague definition or a very beginner's definition of viscosity, but I think it's a good stepping stone to start our discussion on viscosity. Okay, and you will see, like, after some lectures, after some sessions, you will be able to like correctly embrace the proper definition or proper feel of what viscosity means. Okay, so, but for a beginner or very layman, in a layman words, you can just consider viscosity to be a resistive force that resists any kind of motion across the fluid. So if, for example, if you are trying to wave your hand in air, it's quite easy, right? And if you're trying to wave the same motion of your hand inside a bucket of water, you will, of course it's easy, but you will feel that it's a bit more resistive. Water is resisting our hands motion a bit more. And now if you just try to move that hand in a bucket of honey, I don't know how you'll get the bucket of honey, but for example, say if you're doing that, then you will see that it's much more difficult to move your hand in the honey than compared to water. Of course, it's far more difficult in comparison to the motion in air. So from that, from this chronology, you can just understand that, you can easily conclude that the viscosity of air is comparatively lower than water, or considerably lower than water, because the resistance was much more lower. Similarly, the viscosity of honey is higher than water, because again the resistive force of honey was higher than in water. So that's the basic understanding of viscosity. But as fluid mechanics students, we would like to look upon it on a bit more detail. Okay. So let me ask a very general question. Is there a fluid in world that has zero viscosity? Yes or no? Yeah?
No.
Okay. So one says no. Others, what do you suggest? Yes or no? Can there be a fluid of zero viscosity? Others, would you like to contribute? No. Okay. Ashok says no. Anjali says no. Patrice, Power, Rabindra, Shubham. So okay. So I think you can answer. Of course, I won't stop it. But I think you get an idea that of course there's no fluid in the world that has zero viscosity. Okay. But you will see that in this course itself, we will consider some scenarios of inviscid fluids. Okay. Sorry, inviscid flows. I'm sorry, I must clarify, inviscid flows. Okay. So in that case, you might ask a very valid question, like if there's no fluid that has zero viscosity, why we are studying about inviscid flows? Okay. So the thing is, there is a concept known as the boundary layer. Okay. Which we'll discuss, of course, in this course, in the end of this course. So there's a scientist named Prandtl who found out that even though the flow is viscous, the effects of the viscous effects of the flow tends to be very very limited to a very small area. Okay. So for example, if you consider the flow over this plate, let me just give an example. The viscous effects, Prandtl found out that it's only limited to very small area, very close to the plate. Okay, and of course that is because of the viscous nature of the fluid and the friction between this flow and the plate. But other region, that beyond this small region, this region can be essentially be considered as inviscid. Inviscid in the sense that the viscosity is not zero, but the viscous effects or the velocity gradients are so small that the viscous nature of the fluid is not perceived in that region. Okay, so in that way, the inviscid flow becomes relevant. So for example, if you are considering flow over a car, and then okay, I think I have to draw a small drawing, very very bad drawing. Okay, very very bad drawing. But say if you are considering motion over a car, and of course there will be boundary layer generation. Again, so sorry for these jargons that I have not already discussed, but just bear with me. I think when we reach the later part of the course, these discussions will become quite handy. Okay, so in this region, Prandtl said that it is within this region that the viscous effects are dominant, but all the regions beyond this, that is this region and all the regions beyond this, can be essentially considered as inviscid. Okay, so if we are able to model the flow without considering the viscous effects, and we're just interested in those regions where the viscous effects are not present, so again the implication of the car's motion is felt regions in regions beyond the boundary. Okay, and if we're able to solve those flows in those regions beyond the boundary layer, considering the simpler inviscid forms of the governing equation, then it's a good, a good result, right? It's a good compromise. Like we are not correct solving the equations explicitly or correctly, but look, I won't say. I think I have to rearrange my words. We are not completely solving the flow by considering every viscous effects, but we are solving a considerable amount of region which can be essentially be models in viscid and be solved in a much more simpler manner. So I think that's a good compromise. Okay, so that's why we have the concepts of in-viscid flows. But you're right to point out that there is no fluid in the world that is in-viscid. Okay, so thanks for pointing out, and let us now come back to our discussion. Okay, so for this plate again, so when we consider a flow to be viscous, there is a phenomenon known as the no-slip boundary condition. Okay, so no-slip boundary condition basically means that if a fluid, if there's a flow across this a plate, we are considering plate for simplification, of course. So if there's a flow across this plate, the no-slip boundary condition essentially means that there will be no relative velocity between the the fluid particle and the plate, or specifically there will be no relative tangential velocity between the fluid particle and the plate in this region, that is where the particle is attached with the plate surface. So that attached particle won't have any kind of relative motion with respect to this plate, tangential velocity. Okay, so that's what no-slip boundary condition basically means. Okay, so sometimes say, what about the normal velocity? So we don't, the no-slip velocity, no-slip boundary condition does not, what to say, uh, takes care about these normal velocities. Okay, so there's some another boundary condition, that is the no penetration boundary condition, that tells us that the normal velocity of the fluid flow particles at the surface or the boundaries are 0. Okay, so no slip boundary condition only takes care about the tangential velocity. Okay, I hope that is clear. Again, when we solve some examples, it will be much more clearer. So I think for the sake of saving time, I will just skip past this again very elaborative discussion and good discussion about scenarios where the flow can behave as in-viscid. So Professor Chakraborty takes the example of carbon nanotubes, which have very highly slipping surfaces, where there might be slip at the boundaries. There might be relative velocities between the particles and the surface at the boundaries. And he also discusses about the scenarios where the no slip boundary conditions may not be valid, or the slip velocity might occur. So he discusses about the phonetic motions, thermophoretic motions, and electrophoretic motions. And just to give you a head start, if any one of you is interested to look upon the profile of Professor Chakraborty, like if you want to do a PhD or masters later under Professor Chakraborty or his students, just to say, Professor Chakraborty actually works in this kind of flows, specifically this electrophoretic motions, like looking into scenarios or flows where the flow is driven by electric potential. Okay, and his student and him has found out a scenario where actually the particles tend to have a slip velocity across the boundary layer. Okay, again, I think it's too much for you to handle, but if any one of you are interested, you can just look into his profile in Google Scholar. Okay. Okay, so let us again just go through it once. Briefly go through it. So I discussed about boundary layers. So again, there's a very simple, or again a very beginner's definition to a boundary layer, but again it's a very accurate one that is usually being used for most of the boundary layer studies. Okay, so when there is a flow across a flat plate, you will usually encounter a boundary layer which has similar shape of this, like it is 0 at the thickness of the boundary layer is 0 at the leading edge, that is the start of the plate, and it tends to continuously grow. Okay, but what's the formal definition of boundary layer? With what, like, how can we define this green line? Okay, what is this green line actually does? So this green line is the region where the flow velocity is 99% of the free stream velocity. Okay, and again there might be doubts, why 99%? Okay, just to give you a very simple answer, that it's not explicitly taken as u infinity. Why? Because if we do that, then the boundary layer will be like as thick as 1 kilometer, or it will go up to infinity. Okay, so because the effects of plate will be felt for very far distances. Okay, and For the analytical studies, I think it's not a good thing to have a study where the effect of the object is essentially felt up to say 10 or 1000 times your characters in length scale. Okay, it's not appreciable. So I rather have 99% of my velocity and have a thin boundary layer rather than having 100% of my infinity velocity and have a 1000 times 10,000 times thicker boundary layer than our character's length scale. Okay, so that's why we do that. We'll have the elaborate discussion about this when we discuss our boundary layer, so kindly bear with me, but for now that's why we do that. Okay, so that is what has been discussed here. Like there must be a mechanism by which the momentum disturbance is propagated by the fluid, and this momentum disturbance is essentially being propagated by the viscosity. Okay, so viscosity is the factor by which the effect or the presence of this plate is felt by the fluid. Okay, so lower the viscosity, thinner will be the boundary layer. Higher the viscosity, thicker will be the boundary layer. Why? Because lower viscosity will mean that the flow will very faintly feel the effect of plates. So like the boundary layer will be very thin, like the disturbance from the plate will propagate to a very small distance. That's why the boundary layer will be very thin. And for higher viscosity, again the effect of plate will be felt to a very long distance, very long distances. That's why it will create a thicker boundary layer. Okay, for now I will just say, for now just take it as it is. Okay, we'll discuss this thoroughly when we discuss about the boundary layer. Okay, I hope it's a good compromise. Okay, so let us try to proceed further. So okay, let us just go through it once. Okay, so this example was again taken by Professor Chakraborty in a way, considering that what he did was he considered that the disturbances from the plate to the flow actually propagates in layers. Okay, in a way that, let me just show it. Like for example, this is the first layer of fluid that is being attached to the surface of a plate. Okay, so if there's any confusion, let me know. Okay, so this is the fluid molecules, or the region of, or the number of, or the amount of molecules that are attached to the plate. Okay, I'm just looking at a specific region. In reality it should be the entire plate, right? It should be the entire plate, but I'm just looking at a particular region. Okay, then what would happen is that the layer above it, okay, the layer above it will tend to have a higher velocity. Okay, why? Because the one that is closest to the plate or attached to the plate will have of course have zero velocity, but of course the particles above it feels the effect of the plate, which tends to slow it down, of course, but also it also feels the effect of the incoming flow that tends to pull it along with itself, right? I hope this is understood. Okay, so if not, then just let me know. Okay, so similarly the layers above this will again have a profile where it will again have a higher velocity. So these layers will tend to have higher velocity. So what would happen is that, for example, if you consider this layer, yes, understood sir, thank you Ashok. So for example, let us consider this layer, like say layer number 3, this layer. So what would happen is that the layer below it, so layer 2, will tend to slow down this particular layer of fluid, but the layer above, this layer 4, will tend to accelerate this fluid layer. Okay, so it will always be in a junction where the lower layer is tending to push it along this direction and pull it along this direction, and the upper layer is tending to pull it along this direction. Okay, so there would be this kind of motion and you can understand that this kind of force will tend to create a certain couple. Okay, will tend to create a coupling force. I think it's a very wrong terminology, but specifically speaking, it will tend to create a couple. Okay, or basically it will tend to create a deformation of the fluid layer. Okay, so that's what being used as a understanding to consider this derivation. Okay, so he does the same thing. Let us consider a fluid layer here. The upper layer tends to move at a velocity higher than the lower layer, so there must be a deformation of this kind which tends to pull the upper layer at high velocity, and the lower layer will tend to slow it down. Okay, so I think for the sake of saving time I can skip the explicit discussions of how we came into these derivations. So it's very simple. Like for example, if the fluid particle has moved from A to A and its velocity was u, then from A to A it will travel a distance of u times delta t. Okay, it's very simple. Forgive me, I'm not doing it elaborately. Upper layer, since it's moving at higher velocity, so it will move a higher distance of u plus delta u times delta t. Okay, and let us consider the fluid layer to be a thickness of delta y. Then if the displacement of if this distance, let me say b dash, I think, if say this b dash and d dash are very very small, okay, this distance b dash and d dash is very very small, then tan theta can be then we can write tan theta as tan theta as u times delta t by delta y. Okay, if you take the difference, then tan theta will be perpendicular by hypotenuse, so it will be u delta t by delta y. So if this delta t and delta t, if delta t is very very small, then you can approximate yes. So as I mentioned, if this delta theta is very very small, then you can approximate tan theta to be delta theta. Okay, so this tan theta by delta t, let us find the rate of change of this angle. So delta t by delta t, sorry, delta theta by delta theta can be represented as limit delta y tends to 0 delta u by delta y, because we need to like if both of these sides are represented as differential, then we have to consider this side to be differential. We have to have delta y also tends to 0. So we can write this as delta u by delta y. Okay, so what this shows is basically the angular deformation. Okay, so angular deformation for this fluid layer is basically given by delta u by delta y. Okay, so this angular deformation or rate of angular deformation is also known as the rate of shear strain. Okay, and we would like to see that how the shear stress varies with this rate of shear strain. Okay, so if you recall, in the last class we discussed about shear stress, what it is. So we want to see how the shear stress in the fluid now varies because of this rate of shear strain. Okay, now you know where the shear strain will come. Okay, so I hope the picture is much more clearer now why we were discussing that. And this study on relation between how the shear stress varies with the shear strain, or what is the functional variation of your shear stress with the shear strain, is known as the constitutive relationship. Okay, as it is given here, and you can of course tend to create a analogy between this and the Hooke's law, okay, in the solid mechanics, where we find the relation between the stress and the strain, where strain, if you remember, strain is your independent parameter, and we'll see how the stress varies with strain. Okay, I hope it is clear till now. I would like to complete this part a bit more, then I think if you had doubt you can ask. Okay, so we have a very interesting type of fluid known as the Newtonian fluid. Of course, we need to have Newton in our discussions as mechanical engineers. We cannot survive without him. So he again comes into picture in fluid mechanics as well. So Newtonian fluids are any kind of fluids for which the variation of your shear stress varies linearly with the variation of shear strain. Okay, so basically we want that for Newtonian fluids we have tau to vary linearly as theta dot. Okay, the rate of shear deformation. Okay, and to equate this we use a constant of proportionality that is mu theta, where this mu actually is your viscosity. Okay, so before coming into the Newton's law of viscosity, well, and this is known as the Newton's law of viscosity. Okay, so before coming into it, we were just discussing this viscosity as the resistive force. Now you see that there is again a very specific definition to it. Okay, and if you take the dimensional analysis, I think that you already know how to do, you find that this viscosity has the dimensions of ml minus 1 t minus 1, or you can write in SI units as kg meter per second, or Newton second per meter square, or Pascal times second. Okay, so these are the standard units that is used in the SI unit system. Okay, that is what we usually use in India and most of the Asian countries and European countries. For US, again, the units changes a bit, but for our practice, this would be much more useful. Okay, and we define kinematic viscosity as mu times rho, that is the dynamic viscosity mu times the density, and whose unit is meter square per second. And this nu, again, the definition of nu is again a very interesting, it's a very interesting indicator of physics, flow physics. Why? Because see, this mu is an indicator of the tendency of the fluid to create a disturbance, or if the mu is higher, then the fluid will tend to propagate the disturbances to a further distance, right? As we discussed when we discussing about flow over the flat plate. But density tends to have a characteristic where it tries to what to say have or retain its momentum, retain the higher density, the higher tendency of the flow to retain its momentum, right? So this shows an indicator like if nu is high, you can basically say that the propagating nature, disturbance propagating nature of the fluid is higher than its momentum momentum retaining nature. Okay, so this is what it actually means, and I hope when you try to, in your mind itself, when you try to change the values of this mu and rho for different kind of fluids, you will get an idea about the physics that this nu tries to say. Okay, so I think this is something that you will understand from practice and from your own interests. So, but still, as a tutor for this course, I thought I had to discuss about it. Okay, so then again there's a discussion on origin of viscosity, which again, if you want, there is elaborate textbooks and discussions on it, but I have not looked into it actually, and I have just, for the sake of my studies and for basic and even advanced fluid mechanics, we just look into how the parameters such as temperature affects the viscosity of in liquids and gases. So what it is found that the main factor that is or that generates or originates viscosity for liquids is the intermolecular forces of attraction between the fluid molecules. But in the case of gases, the intermolecular force of attraction are very, very low, primarily because these molecules are very, very far away from each other. Okay, so the main factor that increases the viscosity of these gases is the molecular transfer of this molecular momentum across the gas particles. Okay, and what we see is that as the temperature increases, you can, I think you are able to visualize now that the intermolecular forces of attraction between the particles will reduce. In the case of fluid molecules, it will weaken the intermolecular force of attraction, which will essentially reduce the viscosity. Okay, but in the case of gases, the opposite happens, because if you look from the kinetic theory of gases, I don't again have the explicit expression right now with me, but if you look from that perspective, you will see that the kinetic energy of the gases will increase with temperature. If that increases, the chances of collision between the gas molecules increases as the temperature increases, and if the chances of collision or the rate of collision increases, it will essentially mean that the rate of molecular momentum transfer will increase and the viscosity will go up. Okay, so I hope it is clear till now. So I think okay, so there are some Okay, let me just quickly go through this part. Then I think we have some examples that were taken in the class. I will go through it once, and then I think we can start with the question and answer part. Okay. So, for Newtonian fluid, as I already discussed, this shear stress will vary linearly with strain rate actually. But again, there are some fluids which are non-Newtonian. Okay. So non-Newtonian fluid, again, simple, very very simple and clear cut definition. Any fluid that does not follow the Newton's law of viscosity. Okay. So the variation of stress with the rate of strain will not be linear. Okay. So it can be any kind of behavior, but it won't be linear. So to quantify that, what we do is we say that our shear stress would vary with the power law of strain rate. Okay, so we say that tau varies as theta dot to the power n. Okay, where n is your this power, the power of the shear strain rate. Okay, and one of the very popular examples of non-Newtonian fluid is blood. Okay, so if you try to solve the motion of blood in the arteries using the Newtonian approximation, then I think we will be very far behind in the medical research, right? So we need to model blood using the non-Newtonian relationships, so non-Newtonian constant relationships. So from that we find that for blood, this exponent, power exponent, is 0.7. Okay, so with that we can model this relation, and then we can derive the correct momentum equation for blood flow. Okay, and that's the general practice. So before before discussing this part, I think we can look into this diagram first. Okay, so this is a very popular diagram, and I think which would be available in most of the standard fluid mechanics textbooks. It just shows the variation of your stress with strain rate. Okay, so there is a case for ideal fluid. So ideal fluid, as we discussed today, are the inviscid fluids which has zero viscosity. So if the flow is zero viscosity, then no matter how much you strain it or do it or like move it, there will be no change in the shear stress because it won't exert any kind of shear stress on the fluid. Like, that's why with the with however much you change the strain rate theta dot, your shear stress won't rise, it will remain zero. Okay, the other case is the Newtonian fluid, which is given in by the straight line, because of course it gives linear relationship with the line passing through the origin. So like, however you increase the strain rate, your shear stress on the fluid will increase accordingly linearly. Okay, and the most popular example for this is water. Okay, then there are some special cases, for example Bingham plastic. Okay, this is the one. So this is a kind of fluid like which will flow but which needs a certain amount of initial threshold threshold strain, after which only it will try to flow. For example, toothpaste is a very good example. Like if you just, for example, invert the toothpaste tube and open the cap, it won't come out initially, right? But if you press it for a while, then only it starts to flow. So that pressing is the threshold stress or the yield stress, that real strain that the toothpaste requires to generate the shear stress and cause the toothpaste to flow. Okay, so that's why you see that after reaching this certain amount of stress only it will try to flow. Okay, beyond that it won't flow. Before that it won't show any kind of change in the shear stress. Okay, so then again there are two other behavior, that is dilatant fluid and pseudoplastic fluid. Okay, so dilatant fluids are usually called shear thickening fluids, if I'm not wrong. Let me just check once. If any one of you know, you can of course tell me. Okay, yeah, they are called shear thickening fluids. Why? Because in that case the viscosity increases with the application of shear stress, And for pseudoplastic fluids, these are shear thinning fluids that with the increase of the shear strain rate, the viscosity decreases. Okay. Now you may ask how viscosity is decreasing. Okay. Essentially, we discuss it to be constant. Of course, it's not a constant, but for most of our studies, we'll keep it as constant. Uh, but let us see what I was actually talking about. So, if you remember, this derivation, the Professor Chakraborty usually discussed about the apparent viscosity in these kind of fluids, okay, for these non-Newtonian fluids. So let us see how we derived it. So we have tau to vary as theta to the power n, and then we use a constant proportionality k, say, to be equal to tau equal to k I'm sorry, k times theta dot to the power n. Okay, so if we dissociate it in a way that we can write tau as k times theta dot to the power n minus 1 times theta dot, so we can replace this expression with say mu a, which is your apparent viscosity. Okay, so now if you see, if this power of n, this one, is less than 1, okay, if it is less than 1, then what would happen is that as theta dot increases, if it is less than 1, then the value of mu apparent will go down. Okay, that's what I mean by shear thinning. Like, as we increase the strain rate, your apparent viscosity is going down. Okay, so for these kind of fluids, these pseudoplastic fluids or shear thinning fluids, your n will be less than 1. Okay, and opposite to that, in the case of dilatant fluids, if n is greater than 1, you will see that if theta dot increases, it has a positive power, so mu apparent will increase as theta dot increases. Okay, I hope it is understandable, basic mathematics, so I hope it is understandable. So in that case, if theta dot increases, the apparent viscosity will increase, so the flow will, it will result in the shear thickening of the fluid. These kind of fluids are known as dilatant fluid, which has the power exponent to be greater than 1. Okay, so again there are other two examples as well. There are thixotropic fluid and rheopectic fluids. Like, with time, that if the apparent viscosity decreases, these are known as thixotropic fluids. If the apparent viscosity increases, these are known as rheopectic fluids. Okay. Oh, so now I would like to quickly go through two examples that we discussed in the class. So till now, is there any doubt? I will take, say, 15 more minutes at max to discuss two examples that were taken in the class. I won't dive deep into it. I think it was very elaborately discussed in the lectures. So again, it's not correct for me to repeat it entirely with full depth. I will just revise it a bit. Meanwhile, is there any doubt till now in all the topics that we have discussed? I will wait for, say, 1 minute. I will give myself a rest also. So I will wait for 1 minute. If there's any doubt, you can ask meanwhile. Then if not, we will proceed. No, sir, understood everything. Okay, thank you, Anjali. Others also, I feel that they understood. So just give me a minute. You can also try to recollect what we have discussed. So we'll use those concepts in this examples. Okay, again, this example is already taken in the class. Just for revision, because I think we have a similar kind of example in today's problems, which I will give you some time to solve. Then you can tell me the answer. Okay, I think 1 minute is up. Okay, thank you, Anjali Kumari, thank you. Okay, so let us proceed. Okay, so this example, I think it was again very clearly discussed in the class. I guess for the entirety of a lecture it was discussed, if I'm not wrong, but let us just go through it, a brief overview. Okay. So Professor Chakraborty in this example considers that there is a mass and pulley system, and one of the masses is floating over a liquid gel, okay, or liquid film, as he says, and these kind of problems actually are known as narrow gap problems, okay, and again, or lubrication type of problems, which are again a very separate subject of study in these low Reynolds number flows. So again, it's a, what to say, you can look into it if you're interested, but let's go through it once. Okay, so this is a mass pulley system, and he says that the pulley here is massless and frictionless. Okay, massless and frictionless, and the string are inextensible. Okay, of course, to simplify our problem. So the as a fluid mechanics student, you already know where our main focus would be, right? In this region, right? Wherever the fluid is, I would like to be interested in that region. Okay, of course, the concept of mechanics is also important. That, of course, that we will use to find out the forces that are acting, but our primary focus will remain in this region. Okay, so important thing to know is the narrow gap. Okay, the gap between the mass or this block and the plate is very very small, that is being filled by a fluid, and is basically a film. Like, it's a very thin region, so we say it is a fluid film. Okay. So we use, again, we just draw the free body diagrams of these examples. I must not say that I did it. Of course, this Professor Chakraborty did it, so all credit to him. But let us just look into it. So for the pulley, these are the forces that acts on the pulley. Okay, the tension due to the strings, the reactive forces on the in the center of the pulley where it is attached to the wall, and the mass of the pulley. Okay, so we consider that there are no we consider that the mass of the pulley is 0, which is a massless pulley. So from that we get that the tensions acting on a string are equal. So T1 will be equal to T2. Okay, for again clarification for this, I think you can go back to the video lectures for much more clarification. Okay, for mass 2, that is hanging, we have, this is a free body diagram for mass 2. So again, since this is in motion, okay, this is not at rest, so we will have T2. You can of course do M2 by G minus T2, or T2, you can do any, like you can replace the sign as well, but for this sir used this sign, so we are going with that. Okay, but you can use the opposite sign as well, but they will eventually get the correct answer. Okay, so if you already know it by now, right? So if you do that, then you have to again change the sign of acceleration, that like mass is pulling the string up. Okay, like for some reason if it is moving this side, then again you have to change the sign conventions altogether, but you will get the same answer. But logically, like here we just assume that since the mass is falling down, we'll need to have this kind of motion. Okay, so we have T2 minus M2G is equal to M2A. Okay, we keep the same sign convention. This is the governing equation for this particular mass. And for M1, now since here there is no horizontal forces, so we do not need to balance the horizontal force. Of course, there is no other force acting on it, so this is the force equation for M2. For M1, the FBD would be a bit more elaborative, and this is the block mass. This is the block of interest for our study. So there will be two balances. First, the normal forces and the horizontal forces. Okay. So we'll have the normal forces, the mass and the normal reaction will balance out each other. But for the horizontal forces, we'll see that the tension by the string is balanced or is counteracted by the frictional forces between the fluid and the block of mass. Okay, so if you remember, I said that the important approximation or important points to remember is that the gap between the mass and the wall or the surface is very very small, and it's a very standard derivation, or it's a very standard approximation, that if this is the scenario, we can easily approximate the velocity profile or the variation of velocity to be linear in between these kind of surfaces. Okay, if the gap between the two surfaces is very very small, we can easily and very correctly approximate the velocity very linearly across this surface. Okay, so how we find it is basically a coed flow, which we'll eventually see when we solve the exact solution to the equation. But for that, I think it's better that we don't dive deep into how we got it. but you can just take it for as it is for right now, and we will clarify it when we reach that. Okay, but without that also you can just approximate these things. Okay, even for circular surfaces also, of course, again it's a considered coefficient only, but that case also you can assume the velocity profile to vary linearly if the gap between the surfaces are very small. Okay, so I hope it is clear. Let us then proceed further. As I said, normal reaction will balance each other, so n will be equal to m1g. For the horizontal forces, we will have T1 minus Fr would be equal to m1a1. Okay, where a1 would be dv1 by dt. Okay, v1 is the velocity of the block, right? So we have T1 minus mu v by h a. Now you might ask how we got it. Okay, so I think you already know it, but let us just look into it once. So we have force to be shear stress times area, and shear stress is mu times the velocity gradient times area. Okay, this is from the Newton's law. Okay, so if you just again simplify it, it will be the ordinary differential. So we'll have, if u varies linearly, we say it varies as u y by h. Okay, vy by h. So if you take the derivative of this, you will get v by h a. Okay, so this is how you get it. Okay, and v is the final velocity of the block. Okay, so we get, for mass 2 m2, we got that m2g minus t2 is m2 dv2 by dt. Okay, the important conclusion is that since the string is inextensible, these velocities v1, v2 and v would be equal. Okay, if it was extensible, again it will be different, but since the strings are inextensible, this is the further approximation that we get. And we also get that from the free body of the pulley, that T1 will be equal to T2. Okay, so now what we want is that we want to see how this velocity varies with time. Okay, we want to see, so that's why we need to replace all these other variables such as T2, m2, all these variables in terms of, not m2 is a known, so T2 we want to replace in terms of velocities. Okay, so that's what we will do. So from equation number 2 here, we can write T1 to be equal to m2 dv by dt plus m2g, right? Or then if you substitute this in equation number 1, if I go back here, okay, we just substitute the expression for T1 here, we can easily substitute T1 in terms of the known variables, this mass, viscosity and these things. Okay, so we get this equation is minus m2 dv by dt plus m2g minus mu va times a equal to m1 dv by dt. Okay, now if we just simplify it a bit further, you will get m1 plus m2 times dv by dt is equal to m2g minus mu va by h. Okay, now as I told, we want an expression for this velocity, how velocity varies with time. So if we do that, we just do a simple separation of variables or rearranging these equations so that we get dv by m2g minus mu va by h is equal to 1 by m1 plus m2 times dt. Okay, now if you want the variation of velocity with time, we just need to integrate both of these sides and see how it varies. So again, I didn't do it, so if you want, you can do it. Again, it will be a simple substitution, right? It's quite easy to do. You can do it if you want. So so this is how the velocity would vary with time. Okay, so this is what Prof. Chakraborty told it would be. And for steady state, like if t is for long time behavior, it will achieve a constant value. Okay, like for steady state, we will get that this would be equal, this will be balanced, the tension generated from the falling of the mass m2 would be balanced by the frictional forces. So if you do that, you will get v to be m2g h by mu a, which will be the steady state velocity of this settling of this block M1. Okay, so I hope this is clear. Okay, so let's look into next example. Okay, so yes, I think I can take this example. Okay, I'll just quickly go through it once. So again, this is the example of two rotating cylinders. Okay, so so this is the configuration, that this is the inner cylinder. Okay, in this case the inner cylinder is rotating, outer cylinder is fixed as shown by these jagged lines. So we have that the inner cylinder has a radius of R1 and the outer cylinder has a radius of R2. Our task is to find the net moment or net torque generated in the required to rotate this cylinder. Okay, so that's the basic, what to say, end goal of this particular problem. So what we do is we define the length of cylinders as L and the viscosity of the fluid to be mu. Okay, so forgive me if like I'm sounding quite blatant, because this is the example already taken in the class and I'm revising it only because you will find similar examples that will be given for you to be solved in today's class. Okay, so just to revise the concepts. So we find that the variation of shear stress is given by mu du by dr. Okay, so this negative sign is again because of this approximation or this understanding that the velocity of the fluid increases in the direction opposite to the increase of r. Okay, so since the inner cylinder is rotating, you will see that velocity profile would be something like this, like r increases along this direction but the velocity is increasing along this direction. To compensate that sign, we consider this negative sign. Okay, and you'll see that we use the similar approximation while we considering pipe flows. Okay, when we consider pipe flows, we will do the similar sign convention when discussing the shear stress itself. So consider that this is the elemental area. Okay, and why we are considering elemental area now? See, in this case it is not been mentioned that the gap between the two cylinders are very small. Okay, so if the gap is not that small, we cannot replace the velocity profile with a linear one. Okay, we have to consider, or we have to find the variation. We don't know the variation, so we have to do integration to find the net moment required to rotate the cylinders. Okay, so we cannot assume a linear velocity profile. Okay, so we have to consider velocity to vary with the radius. Okay, so to do the integration again, we need to consider elemental surface, and this is the crucial part. Which is the surface that you should consider? Okay, so any one of you, like you might ask, there can be two types of surfaces. Okay, the cylindrical surface, that can be something like this, that varies that like is along the length of the cylinder, or the circular ring surface, this one. This also surface, you can do the integration across this as well. Okay, but what should be the elemental surface in this case? Can anybody tell? The cylindrical surface or the ring shaped surface? So this is important concept to understand. Like if you're doing integration, you need to understand like which surface you are looking into. Cylindrical surface, exactly. Why? Because since we're rotating the cylinder, see, if you're rotating this cylinder, the moment required to rotate this cylinder would be again the resistive force of the fluid, because of the fluid between the cylinder. Okay, and this fluid is interacting on the cylinder across the length of the surface. Okay, it's not only limited to this particular area, but across the length of the cylinder it is interacting. Okay, so that's why we have to integrate. If we consider elemental surface area, we have to integrate across the length of the cylinder. Okay, so the elemental area in consideration would be 2 pi rl. Okay, where r is the radius of the surface of the elemental surface. Okay, at the radius of the elemental cylinder. Okay, elemental surface in this case would be a cylinder. So to find the moment of F with respect to the axis, that is this axis, it will be F times R, where F is the elemental force F would be this times, or elemental moment, I must say, elemental moment actually, it would be uh, mu times du by dr times 2 pi rl times r. Okay, this would be elemental moment. To find the net moment, we have to integrate it. Okay. So we can rearrange this equation something like du times minus m 2 pi mu l r to minus 2 times dr, and if we integrate it, now, so u would vary from, if you just, let me just give, okay, so if you see this u, if you integrate it, u will vary from outer cylinder here. If you remember the no-slip boundary condition, the velocity here would be 0, correct? But for this cylinder, the velocity of the fluid would be omega r, correct? So because the inner cylinder is rotating at a velocity of omega r, okay, along this direction, I'm sorry, correct? So your velocity would vary from omega r to 0, because we are doing integration from the inner cylinder to the outer cylinder. So like you can do from r2 to r1 as well, then the integration will be in the opposite sign. But if you're doing from r1 to r2, increasing radius, then you will have velocity vary from omega r1 to 0, and if it was moving, then it will be omega r2, okay, but since it is at rest, it will be omega r1 to 0, and these terms, that is m 2 pi mu l, would be constants, and we integrate from r1 to r2. Okay, if we carry forward the integration, it's very simple integration, you will get that omega r1 will be equal to m by 2 pi mu l times r2 by r1 divided r2 minus r1 divided by r1 times r2, and if you find the final expression of moment, you will get m to be equal to 2 pi rl omega r1 square r2 divided by r2 minus r1. Okay, so yes, I think that's it. So the next example, this is the one I wanted to actually take in the class, but I think there is one question that is been given for this exact derivation. Okay, so I think I won't repeat it, but let us look into the questions first. Okay, then I think it would be good. Okay, so I hope the question is visible. Okay, so let us try to solve it. Okay. So for Newtonian fluid, for question number 1 actually, for Newtonian fluid, which of the following options are correct? Okay. We discussed so much today. All of the options seem quite similar, but one of the options is correct. Okay. Ashok says B. Others, can you please point out the correct option? I'll wait for 1 more minute. It's a very basic question, so I don't think we should give too much time. Okay, see, these are the type of questions that you can expect. Like wordings would be quite similar, but we expect that the concept is clear. Okay, Anjali also says B. Patrice also Patrice says A. Okay, so right, so this is where I think the confusions may arise. So of course, for Newtonian fluids, you remember that we correlate stress with strain, right? But I think that is where the mistake usually occurs. It's actually the relation between shear stress and the shear strain. Okay, Lily says option D. Okay, so again, just to reiterate, thanks for the participation, but the correct answer would be option B, because we saw that shear stress is directly proportional to theta dot, and we told that theta dot is the rate of shear strain. Okay, so that's why the correct answer would be B. Again, the discussion why we use shear strain is primarily because there is no resistive force given by the fluid under the application of a constant force, so it will tend to generate a continuous deformation, which is something that is difficult to quantify if we just consider shear strain. So that's why we consider shear strain rate to find a relationship between the shear stress generated in the fluid and the shear strain rate. Okay, so sometimes in the lectures also I might uh, mistakenly just say relationship between shear stress and shear strain, but you can ideally actually correct me that actually it is shear strain rate. Okay, so this is the correct option. Again, I won't dive deep into it why we chose that. For that, I think you can just go back to the notes and class discussions. Okay, so second question, I think you need to do a bit more derivation. If you know, it's fine. So can you tell me the units or dimensions of dynamic viscosity? Okay, Ashok says B. Others, can you try? So let me just give you a hint. It's a basic dimension analysis is Pascal times second for mu. It is the unit. Can you do a dimension analysis for Pascal and second? Like what would Pascal times second would be in terms of mass, length, and time? I'll give you say 1 more minute. I don't think you need much more time for this. Okay, Lily says B. Others, can you try out? Okay, so if you look into it, it's quite simple actually. If you do a simple dimension analysis, you will get to a point that you'll find the dimensions of the dynamic viscosity. Okay, just to not to get confused with kinetic viscosity. So this is the primary what to say confusion usually. So dynamic viscosity or viscosity in general, we would mean mu. Okay, but when we say if you want to represent kinetic viscosity, we will explicitly say kinetic viscosity, which is actually nu, which is mu times density. Okay, so just to look into the derivation, so I hope it is here. So yeah, so if you do the dimension analysis, you will get nu is equal to meter second per meter square. If you do the dimension analysis, you can just go through it once. It's not that difficult. You will get dimensions to be ml minus 1 t minus 1. Okay, so I think we can proceed further. Yeah, so question number 3. Okay, this is the correct answer. For question number 3, the increase in temperature A increases the viscosity of liquid and decreases the viscosity of gas. B decreases the viscosity of liquid, increases the viscosity of gas. C increases the viscosity of both liquid and gas. D decreases the viscosity of both liquid and gas. I think again we discussed it today already. Okay, again I think, yeah, thank you, it's correct. It's B, that it decreases the viscosity of liquid and increases the viscosity of gas. Okay, so I don't think, thanks D, it's correct. Okay, it's option number B. So question number 4, can you just try it out? If a relationship between the shear stress and the rate of shear strain, see they are emphasizing shear stress and the rate of shear strain. Okay, for a general one directional fluid motion is expressed as tau to the power m times, oh it should have been mu, I'm really sorry, mu times du by dy to the power n. The fluid with exponent n less than 1 is known as, we just discussed it, n less than 1 is basically the shear thinning fluid, blood, option A. Okay, nice. Lily says option A. Okay, so yes, basically correct. So it is a pseudoplastic fluid. Okay, so very nice. N was 0.7, right? That's why you said, yeah, it is correct. Yeah. So shear thinning fluid, right? So if you go back to the derivation, just for others to revisit. So if I go back here, sorry for scrolling again, up, down. Yeah. So here, and by viscosity, it is for Newtonian fluid is meant that we are discussing about apparent viscosity, because we are trying to obtain a relationship between the shear stress and the shear strain rate. To do that, to convert this power law to a linear relationship between the shear stress and the shear strain rate, we need to replace this viscosity with the apparent viscosity. So in that case, for non-Newtonian fluids, we will mean viscosity as the apparent viscosity. So we found that the apparent viscosity is k theta dot to the power n minus 1, where theta is a shear strain rate. is equal to mu apparent. So if n is less than 1, it will mean that n minus 1 will be negative. So n minus 1 is negative. It will mean that if theta dot increases, this term, this product will go down, so apparent viscosity will decrease. So this kind of fluids are known as pseudoplastic fluids. Okay. So let us go back to the questions. This question, oh, again, this is very simple. Can you tell me what is the correct answer? Kinetic viscosity dimensions. What will be the kinetic viscosity dimensions? You already found out dimensions for dynamic viscosity. Just divide it by density. Then the dimensions. Mu was ml minus 1 t minus 1 divided by rho. What will be the dimension? Mu is mu by rho. Okay. Lily says it's C, Ashok says it's C, and it is indeed correct. Thank you. So the correct answer is C. Okay. So if you do that, you will see that you will get ml minus 1 t minus 1 divided by L times, sorry, not L times, it will be m times L cube. So if you do that, you will get L squared t minus 1 or meter square per second. So if you even recall the dimensions of kinetic viscosity, which is meter square per second, you can easily say this L square by L square times t minus 1. Okay. So next question, it is quite lengthy, so I think I will give you some time, say around 5 minutes to solve it. Okay. It's not that difficult, but I think it will be the first question that will take some derivations and discussions. Okay. So let us look into it. A cubical block weighing 1 kilonewton having a 100 millimeter edge is allowed to slide down an inclined plane making an angle of 30 degree. Okay, inclined plane is an angle of 30 degree with the horizontal, on which there is a thin film of liquid, a Newtonian fluid in nature, and having a viscosity of 0.202 Newton second per meter square. Okay. So if the thickness is estimated to be 0.02 millimeter, the terminal velocity of the block will be question mark. Okay, it's an interesting question. So I'll give you 5 minutes. Okay, so I'll just draw a schematic diagram of the question. So this is the block. So it is the inclined plane, which is 30 degree. Okay, and there is a block of certain mass is 1 kilonewton. Not mass actually, weight is 1 kilonewton, and there is a liquid filled in between. Okay, it's a liquid film in between this region. Okay, it is falling down in this direction. Okay, so you have to find the terminal velocity of this falling block of falling block. Okay, so thickness of the film is 0.02 millimeter, length, or basically it's a cube, so the edge length is 100 millimeter. Okay, and the viscosity, that is mu, is equal to 0.202 Newton second per meter square. Okay, so these are all the things that you already need to know, and it's a thin gap. I think it's already mentioned, thin film. Okay, thin film. So if you remember, for thin film, you can usually approximate a linear velocity profile. So with that idea in mind, you can try to proceed and solve this question. I'll give you 5 minutes, so I will wait till 7:47, 7:48 actually, and then you can let me know. Okay, try it out. just one more concept. I think it's important because just to let you know, like for terminal velocity, it will basically mean that there's no force acting on the no net force acting on the block. So it would mean that all the forces that are acting on the block are balanced by each other. So if you see, the only force that can actually make an effect are the tangential forces. Okay, 100 divided by 0.02. Okay, Patrice says D. Okay, so others, let me just see whether it's correct or not. So others, I cannot say the answer, Patrice, so I hope you can kindly wait for 2 more minutes. Others, can you also try and tell us what will be the answer? Okay, thanks, Patrice. So others, kindly wait, kindly try it out as well. Let us look into them together. So as I was saying, so when it reaches terminal velocity, it will basically mean that the tangential forces are balanced. So the tangential forces that are acting in this particular block are the gravitational pull of the block in the downward direction or along the direction that is shown here, and the frictional forces. So the frictional forces would be balanced by the gravitational forces, and if you equate those forces, you can find the velocity for v. Okay, so that's what the logic is, and that's the concept of terminal velocity. So if you say that someone is falling at the terminal velocity, so it will basically mean that they're going under free fall. So the air resistance is basically balancing the mass of the person or the object. So that's why they're saying that it's going under free fall. Okay, so that's where they obtain the terminal velocity. So that's why they fall under a constant velocity. Right? F equal to ma, or m times dv by dt. If v is 0, dv by dt is 0, so f would be equal to 0. Net force would be 0. Doesn't mean that no force is acting, but it means that the net forces are balanced actually. Okay. Forces are of course acting, but they are balanced. So 1 more minute. I think the time is up. So sorry. Okay, I'm really sorry if it seems a bit rushed, but I think there's one more problem, so I will give a bit more time there. Okay. Sorry for rushing, but let us look into the answer. And Patrice, it was correct. Just to let you know. Let us proceed. Okay. So let me look into the solution. Sorry to others, like if it feels a bit rushed, but let me just look into it. Okay, so this is the question that I was mentioning. This is the schematic diagram of the problem. So weight, if you remember, always x along the downward direction. Okay, always x perpendicularly downward in the perpendicular downward direction. Okay, so we need to dissociate it into its components. It's a very standard problem in mechanics. So this will be w sine theta, there will be w cos theta. Okay, very simple. So we'll have that the gravitational forces will balance the viscous forces. Okay, and for viscous forces we find that again tau is, let me just write it, tau is mu du by dy if u is v y by h. Okay, this is the standard velocity profile for thin gaps. Okay, you can just write it down or for your reference as well. So if you take du by dy, it will be v by h. So tau would be mu v by h. That's what we have taken here. So we replace it here. So we have tau mu v by h times L square, where L square is your area at which the viscous forces are acting. So this will be balanced by w sine theta. Right, so if you find the velocity from this expression, like just take all the terms here and find the expression for velocity v. If you substitute the values of all the terms given here, you will find that v is equal to 5 meter per second. Okay, so I hope this was fine. Let us look in the next question. Others, it's fine, right? Okay, so this is question number 7. I think this is the last question today. So this is the question, actually the example that was taken by Prof. Chakraborty. So if you remember the example, perfect, or else you can just try it out. Okay, so the question is, question is, a circular disc of radius r is kept at a small height h above a fixed bed by the means of a layer of oil of dynamic viscosity mu. Okay, I think it's simple derivation, not numerical problem. Okay, the disk is rotated at angular velocity of omega. Assume a linear variation of velocity within the oil film again and ignore the edge effects. The viscous torque exerted by the oil on a disk will be question mark. Okay, so to help you out, I hope the question is clear. Okay, just to help you out, I think I will just go back to the diagram. So this is the schematic representation of the diagram. Okay, I think this is, yeah. Okay, so this was the example taken by Professor Chakraborty already, so that's why I did it, but this is again a question, so we have to deal with it. Okay, so this is schematic representation. We need to find the expression for torque. Okay, torque basically would be dF times R. Okay, so the disk is rotating at the velocity of omega. Okay, and the thin gap is here and this height is h. Okay, so now the only key difference between this example and the other example that we did for the cylindrical one is the again area that we choose for doing the integration. If you remember, in the case of the previous example, we chose the elemental area to be a cylinder, but in this case, since the variation is across a circular surface, across the surface of this disk, the elemental area would be a circular ring. Okay, and elemental area of this kind of rings are given by 2 pi r dr. Okay, the expression for torque, the shear stress would be mu v by h. V would be omega r. Okay, by thin gap limit, the velocity would be the linear velocity, so it will be mu v by h, and velocity at a section r would be omega r, so it will be mu omega r by h. So this is the hints that I'm already giving you. This would be the expression of moment. From all these hints, I think you can easily find the expression for the torque. Okay, so I'll give you say 3 more minutes, because you just have to do the integration now and apply the limits of integration. So in 3 more minutes, just let me know the answer, and then I think we can call it a day for today. Okay. If the diagram is clear and if you noted down this, I think I would like to go back to the options there so that you can just take the reference. Okay, I think I can write it down, like I'm just waiting, so I think so option A would be pi mu omega r to the power 4 by 2h. B would be pi mu omega r to the power 4 by 8h. C would be pi mu omega r to the power 4 by 16h. D would be pi mu omega r to the power 4 by 32h. Okay, so it feels that you already know that your numerator would be the same, pi mu omega r to the power 4. It's only the denominator's constant term, that is 2, 8, 16, 32, that difference, it is different. So I think it simplifies the solution even further. So okay, so you have 1 more minute, I think, for the integration. Do the integration and tell me the answer, then I think we can end the class for today. Just integrate this expression. Actually, there's nothing more complicated. Just integrate this expression. Of course, substitute this here, then you get your answer. Limit integration would be from 0 to r. Okay. Is it option A? Yeah, okay, thanks Ashok. So it is correct actually, so it is option A. Okay, so thank you. Others also, I definitely know you all have been trying, so sorry that I had to rush. So it's very simple. If you just do the integration that is shown here, you'll get that m is 2 pi mu w by h r to the power 4. If you just cancel it, you'll get m or the torque to be pi mu omega r to the power 4 by 2h. Okay, so yeah, that's all for today. uh, Thank you again for attending today's session. So it was a very much more interactive session than the first session, so thank you for it. Let's all meet again today. Let's all meet next week. Okay, thank you then. I'll end the session so you all can leave. Okay, thank you so much, Patrice. Okay, then I will end the class today. Okay.